Depends on that side.
Okay, great. So our talk today is by Kareljan Schoutens from the University of Amsterdam, and he's going to speak about supersymmetry and integrability.
Okay, thank you. Sorry for this hassle in starting up. I'm very happy to be here. I try to adjust my style, to the mathematical nature of this place and this workshop. But I'll alternate a bit between more and less rigorous statements as we go along. My first point, I want to make sure you get me when I say supersymmetry. What I mean is this here. So I'm going after systems with Q's and Q daggers, which are supercharges, such that if I anti-commute them, that gives me my Hamiltonian. So if you wish, this is baby space-time supersymmetry. Space-time supersymmetry, you get all the space-time symmetries from supercharges. Here I only get time translation, so it's if you wish supersymmetric quantum mechanics, and in certain cases, depending on where we are, if we go to a scaling limit, you'll see full space-time supersymmetry emerging. For example, many 1D systems give you in the end 1 plus 1D actual superconformal space-time symmetry, but that's to be gained. It's not obvious that this always comes out like this. Now, just as a disclaimer, sometimes in condensed matter, people speak about supersymmetric TJ, supersymmetric this and that. That's different stuff. Those are lattice models which have, let's say, a Lie superalgebra symmetry. So there are some symmetries that look like my Q's and Q daggers, but if you anti-commute those, they simply give you another symmetry, some SU2 or whatever, rather than the Hamiltonian. And then a lot of the magic that I will be discussing today never happens. So the essential difference between these kind of things, which are sort of more traditional, so to say, and my situation is that I really get my space-time, my space translation, my time translation, sorry, my dynamics from the supercharges. So this is what will always be, behind everything I show today. So here's a bit of a catalog of things I'll have in mind and bring up in more or less detail. So the basic thing I'll be bringing up all the time is what we call this M1 model, which is very general. So you can define it on any graph. So whatever graph you have in mind, you can do it. If you go to 1D chains, it becomes integrable, critical. You can do integrable perturbations and make it massive. You can connect to field theory descriptions. I'll discuss all that in a bit. And then if you go to higher lattices, let's say 2D to begin with, you get quite remarkable stuff, which we call super frustration. So I'll show some of that as well. And probably there's much more of this type to be found, but I'll focus on this situation to make that point. In 1D, we extended this stuff with Fentley, who's my main collaborator on these things, and Bernard Nienhuis, to what we call MK model. So we somehow introduced this number K, which, if you make a quick jump, actually gets you in the critical situation to much more interesting critical behavior. So you get minimal models of superconformal symmetry with label K, which for the experts would mean you get things like parafermions and much more internal dynamics to these systems. So these are quite rich models, and I'll spend a lot of my time actually on this number 2 model in this series to make several claims and points over there. Then there are some other models which came up, which are similar but also rather different. So one is a model I cooked up again with Paul, where we took 2 free fermion chains, just plain free fermions, no spin, propagating on the chain, and then we coupled them in a funny way. And we observed that if we do that, we got supersymmetry, and we got some strange properties. So the Hamiltonian for this situation would be standard fermions on the chain, and they're coupled in a funny way. So there are 2 coupling terms. One is simply density. So if J and J plus 1, let's say like here, are both occupied, there's some energy for that. And then there's another one which is telling you that you get certain interactions. If you hop from, let's say, here to here, past an occupied site on the other chain, and there's some funny complex amplitude for that coupling. So this comes from somewhere, which I won't go into here. But it turns out if you make this setup, the whole thing goes supersymmetric in a rather remarkable way. And this in a sense, the interpretation in the end is that the fermions on the top chain would be like semions of, let's say, fermion number -1/2. On the lower chain +1/2, and the supersymmetry would actually transfer you from one chain to the other. And if you anti-commute 2 of those, you actually start moving on a single chain, but you have the interactions that are a remnant of the supersymmetry construction. There's another model which actually is turned out to be very close to this in its mathematical structure. This was published a few months ago by Jan de Gier, Bernard Nienhuis, and collaborators, which is a single chain model where there's again my situation, H coming from Q dagger Q. And now the Q does a funny thing. It either puts extra particles on the chain or takes them out, but in a funny way. It only puts particles if there's two empty neighbors with these projections, so like this. Or it takes out particles when there's two occupied neighbors. So the whole thing is particle Hall symmetric. Doesn't preserve a particle number. And if you take this magical combination, you square it, you again get a supersymmetric model with interesting properties. And it turns out to be mathematically very similar to this coupled chain model. That's not obvious from what I show you here. But for example, the Vedant's solutions are very similar. Okay, so these are some of the models that have been discussed. There's some others as well, but I think this is enough for today, for sure. So now before going into complicated things, there's a few basic things you learn as soon as H equals Q dagger Q is in place. This is in a sense, Witten 1980 something, some sort of quantum mechanics. So what are those things? Well, it's really very simple. It's almost embarrassingly simple, and it's quite surprising you get so much out of this in the end. So here again we go. So there's these two Q's, one is the dagger of the other. They should be nilpotent. That's to get my game started. I usually have a fermion number n sub f, which gets increased by 1 unit by Q dagger and decreased by 1 unit by Q. The one exception is this particle Hall symmetric model of Nienhuis and company, where they do have -1 to the n f, but not n f itself. They break that symmetry. So now the Hamiltonian again is this definition, and if you write two lines, you will conclude it commutes with the two supercharges and also with the fermion number in this case. Okay, so it acts within a given fermion number, and it has this supersymmetry for free.
Typically, in this context, you generate two Hamiltonians, right? So superpartners also Hamiltonians. How does it work in this case?
Well, I guess you can do the Hamiltonian restricted to even or odd parity, which you can call two different things, or that's probably, but I give it one and the same notation. Okay, so if you have this and this alone, what do you learn? Well, a few basic things. Again, this is really very, very elementary. First of all, your energy is all positive or zero, because essentially H is a square. As soon as your energy is positive, there's always doublets, because if you have a state psi, say, which is an eigenstate, you make a partner. You can always tune it such that it's killed by Q minus, say, but then it has a partner that you make using the Q plus. The only exception is that you cannot make partners if you're at zero energy, because then you're killed by both supercharges, and you're all alone. You're a singlet on the supersymmetry, and it's either one or the other. Either you're at zero energy, you're a singlet, or you're a doublet, and that's it. So all these spectra of these models have this common structure. So one more thing, which this is the W Witten index. This is a magical number that you use to analyze your spectra. So it's simply the trace of -1 to the fermion number, and so you do a full partition sum, but you keep track of minus signs for, let's say, states with odd numbers of fermions. That's usually an easy thing to compute, and much easier than solving your Hamiltonian, so to say. And now the funny thing, which is quite obvious, if you have these doublets, these two members of a doublet differ by their fermion number by +or -1, which means they will cancel in this trace. That's kind of obvious. So the trace only is supported by the zero energy states. Right, so that's very simple. And that means, for example, suppose you evaluate your W, it comes out to be 10, that means that there have to be at least 10 of these guys in your spectrum, because all these guys up here can never contribute to the Witten index. So this way, you have a very cheap strategy to actually discover facts about zero energy ground states of this system. And that's one of the magics of supersymmetry. Computing W is usually easy, but it tells you information about strict energy zero ground states of a Hamiltonian, which is usually not so easy to get.
This eventual degeneracy can be understood according to other things or purely accidental. I mean, if it's 10 or 21, I'm learning something, or I shall take
it depends. I'll have many of these numbers coming up in a bit. Sometimes they're kind of obvious where they come from, or we understand it from CFT or from basic mathematics. Sometimes there's big mysteries, and we can't even count them. I'll have a few examples in a minute. So let me continue. But so here's an example of the typical spectrum that you have. This is this simple model, 6-side chain, very basic. If you compute W, it's actually 2. So here you see the spectrum. So I plot NF here, fermion numbers 0, 1, 2, 3. These are the energies, and you see lots of doublets. These are always paired, one extra fermion added by supersymmetry. The only exceptions are these guys down here. In this case, there are 2 of them, which are singlets on the supersymmetry. And this kind of structure is imposed on you as soon as you have H equals Q dagger Q, always. So it's as simple as that. Now, of course, this is the interesting corner where you have stuff, you know, by supersymmetry you have easy access to at least counting how many states you have down here. And you know, this is kind of the benefit of using this formalism in the first place. So let's look at some of those supersymmetric ground states, and let me give you some facts about those. So M1 model, this basic thing, I'll define it a bit later. On a closed chain, there's a number of three, a multiple of 3 for the number of sides, you get 2 ground states. I showed an example just a second ago. That's already slightly remarkable. It's not 1, but it's 2. 2D square lattice, let's put M1 model on that. Let's make it periodic, and by n, you know, on a torus, these are the number of ground states. You know, it's already sort of remarkable sequence of numbers. Not sure if you can see what those are.
How they are ordered?
This is 1 by 1, 2 by 2, 3 by 3, 4 by 4, etc. So there's something going on here. 2D triangle lattice. Let's try that one. I don't know. I mean, I don't have the number of ground states strict, but I have these width indices, which are much easier to compute. So they're lower bound to the number of ground states. If I do, you know, let's say 6 by 6, width is 102, and this grows, you know, exponentially fast.
Is there some periodicity in this sequence?
Here, I'll come to this. Actually, these numbers we understand, and I'll give you the secret for those. These we don't understand at all, but we do understand that they grow exponentially.
How do you compute them?
These are width indices which we compute by brute force numerics. I'll show a bit more later. But just to warm you up that, you know, these numbers are kind of spectacular. Back to this MK model 1D, then, you know, it's more tame. If you put this MK model, you go to K plus 1 ground states, which actually is a significant number, which some people we've recognized. This is the width index of the number K M1 model of superconformal field theory. And then these pair models, so these coupled Fermi chains, or this recent particle Hall symmetric model of Nienhuis and Jan de Gier, they're again different. For example, these coupled Fermi chains on 2 L sides give you 2 to the L ground states, which is again a strange number. And for this particle Hall symmetric model, here's a table I stole from their paper. You know, it's pretty much 2 to the L-ish, but with details. So it grows, but in a kind of funny way, and you know, they keep track of that. Now, to tell you a bit more about how this goes, and you know, to show at least one set of Bethe equations, to be good to this workshop, this is actually rather easily understood. It turns out if you write the Bethe equations for actually both of these sort of Cooper pair type systems, they look something like this. So there's one level of nesting, and now the whole thing is such that, you know, at the second level, you know, if you add a pair U minus U, you don't affect the top level at all. So you can add, you know, lots of pairs U minus U at the second level and keep, let's say, free fermion relation at the top level. So in a sense, you know, these are zero energy states that you can add, they're like pairs. So you can kind of, you know, rain extra Cooper pairs on these free fermion states without affecting the energies and build up, you know, 2 to the L type degeneracy. So this is, in that sense, it's rather easy, although the details are not so easy. As you could see from this table that I showed, that there are some irregularities there. But this is a funny thing, and supersymmetry alone doesn't give you this 2 to the L. There's something else that you need to analyze to learn about this. These things, by the way, are probably not conformal. If you look at the gap between all these ground states and the first ground states, it's like 1 over L squared. So these are, you know, kind of anomalous, non-conformal 1D systems. So I wouldn't say too much more about these here, but there's rather interesting structure to be studied there, to be learned about. So I'll return now to this basic thing, this M1 model, which in a sense has the essential information. How do we define that? So take your favorite graph, can be anything. Define a Hilbert space by putting spinless fermions. Just, you know, these blue balls are my spinless fermions. And with one rule, which is the essential workhorse of the whole construction, I don't want particles to sit next to each other on the lattice. So as soon as there's a link on the graph between 2 sides, I forbid this kind of configuration with both occupied. Okay, so this is, if you wish, an infinite repulsion between nearest neighbor sides. So I use that by simply cutting out those states from my Hilbert space and make a reduced Hilbert space. Okay? Now on that Hilbert space, I take the most obvious particle creation operator that I can think of. I simply write this here. So I take my Q dagger, my supercharge. It tries to put a particle everywhere, so I sum over all sides C dagger I. And the only thing I have to be careful about is to avoid putting a particle next to an occupied site, so I put 1 minus n for all the neighboring sites. Okay, so I really, once I have cut out the undesired configurations, I simply say, now I add a particle in this restricted space, that's Q dagger, take out a particle, that's Q, and then my H, as always, is Q dagger, Q anti-commutator, and that's it. So this is essentially, it's almost trivial, but it turns out to be rather rich in its structure, as I already showed you a bit. If you do this on 1D, you can work it out, you pick up some hopping terms, because some of the C's of the Q dagger can talk to the 1 minus n's of the Q. So in the end, the Hamiltonian is a hopping term, nearest neighbor hopping, again protected by these projections on two sides, and some interaction. So you're forbidden to be next to each other, and if you are 2 sides away, there's some extra potential energy there.
This will be updated by Kareljan Schoutens.
It's close to that, right? It's close to that, yeah. So so you can do, this is very close to actually Z-type models, where you can also imagine forbidding, for example, nearest neighbor sites to be occupied by spin-up pods, etc. But you see, this is like a TV model, I think it's called in standard language, with a tuning, right? So this interaction needs to be tuned in its strengths to the strength of the coupling. If you violate that, you do the supersymmetry.
So there are no coupling in that Hamiltonian?
Pretty much no, because my Q doesn't have any free parameters, so my H same. So the coupling is fixed, and also the chemical potential is fixed. So in that sense, I'm tuning myself in a corner to have the supersymmetry work for me. Okay, so now, just to be sure, this is close to trivial, but to show you again this 6-side thing, let's simply count on our fingers to show you how this works. So let's do this with an index, right? So,
Excuse me, if you,
yes.
instead of giving a really hardcore repulsion straight away, 0, 1, can you relax a little bit? Put something which, I don't know, either with probability or with...
sure, but I guess...
Is still supersymmetric, or you violated...
You see, if you leave out the constraint and you write my Q's, they are simply a Clifford algebra, Q equals unity.
Yeah, exactly.
So nothing happens, and I think if you do it in a softer way, you break supersymmetry. So my framework is extremely restricted, so I need to tune all kinds of things to be in the situation.
For your supersymmetries, once you assign the charges, you have the Hamiltonian, nothing to check. Anything is a rule of game. It's not you define the charges,
Right.
and then you have the Hamiltonian. You have not to check anything.
You have to check Q squared equals 0, right?
Yeah, so that's the game you play. But you see, if you go to, for example, these MK models, there's lots of different amplitudes in these supercharges, and you can play with relative strengths of those to tune into out criticality. You can stagger the sides without breaking supersymmetry. So there's things you can do, but this M1 in its most basic form is completely fixed.
So if you put 1 minus alpha ni or n delta, I present a new model instead of alpha equals 1, some other alpha. Is that still a supersymmetric model?
I'm not sure if
You still have
the
Q
one thing
squared
you have to
equals
check
0.
is Q squared equals 0.
That's the one you have to check. So that's not trivial, right? You have to check that.
Right.
Q squared equals 0.
That's the only thing, and then you have your new model and you can play with it.
You have to add a few terms, I guess.
Maybe you have to.
So, but let me, go with my very basic thing. This is almost, insulting your intelligence, but still. So let's, just do this model on 6 sides, and let's do this with an index. So, no particle, 1 state, 1 particle, 6 states. 2 particles, there's actually 9 states, because if you put them like one here, you can do 6 choices. If you put like this, you have 3 choices, right? So you have 9 of those. 3 particles, there's 2 ways to do that. And if you do with an index, you get +2. So, this is really, you do this on top of your head, and then this guarantees again that the spectrum has to look something like this here. There's 2 guys sitting down here at particle number 2. Right? So strictly speaking, the counting here guarantees that there are at least 2 ground states. Some of these guys could come down to 0 energy as well, but there has to be at least 2. Okay, now if you have this same model, and now you go to not 6 sides, but let's say 6 million sides. So here's a few quick facts. For example, multiple of 3 sides. W is always 2 ground states at 1/3 filling. So if you do 6 million sides, the ground sits at 2 million particles. Open chains, it's a bit different. You get width of plus or minus 1, depending on how long the chain is. So that can be analyzed. You can do a weight ansatz for this. It turns out you can actually map this in a smart way to an xxz at delta equals minus half. It's essentially the same model, except if you do the mapping and you use xxz language and then you apply a supercharge, actually that changes the length of the xxz Hamiltonian system. So if you wish xxz delta equals minus half is supersymmetric, for example, the CFT that you write for this has supersymmetry. But if you look what supercharges do, they actually change the length of your chain. That's why nobody ever noticed that there's this supersymmetry.
So the Hilbert space is for our length of chain.
Right, so the Hamiltonian preserved the length, but the supercharges don't, so they hop you to another length and back.
But they have to act well on the Hilbert space. Also, you have two lengths of chains. Or no? Yeah.
Yeah. So if you compare two xxz models, you know, L size and L plus one size, and you look at spectra, you'll discover that they're degenerate. And our model somehow has folded these two spaces in the one Hilbert space for our formula. But this came after the fact that this is kind of important to understand. So okay, you can analyze these things further and then draw conclusions. It turns out this model, which doesn't have any free parameters, is critical as you write it, but as a CFT and everything's very standard. So what CFT is that? Well, you know, n equals 2 supersymmetry is manifest, so it has to survive. So you look at the CFT, n equals 2 supersymmetry. Well, there's a list of those. The simplest, labeled K equals unity, is actually C equals 1 theory. So there's an old paper of Watterson, early CFT days, where he wrote that using a single scalar field. That's the quickest way to do it. Single scalar field compactified R squared equals 3. And that's the CFT we're looking at. If you look at boundary conditions, you're looking at Ramond sectors, which is because you're periodic on the chain, which in the CFT on the plane means you're in the Ramond sectors. And then you can make the translation. So for example, if you put F particles on L sides, we look at a U1 charge M of this here. And you can make all these comparisons. So for example, here's an open chain spectrum, 21 sides, 6, 7, 8 particles. Here's a ground state, one single ground state at 1/3 filling, as you see. If you compare this to the CFT spectra that you get from the books, everything has a perfect match, and this FL combination tells you which M's you look at in your U1 modules of this CFT. So this is all very nice, and you can actually go to very small systems like 20 sides, and you see these conformal structures quite manifestly. 1, 1, 2, 3, etc. This is already visible in very small systems. So that's
how is the Witten index of the lattice model manifested in the continuum limit? Do you have these ones have Witten index 1 or something?
No. So the
identity
number
operator
K,
or something?
minimum model of CFT has K plus 1 for Witten index, which actually we see if you put it on a closed chain of the right length. If you put it on an open chain of some length, you actually lose some sectors, so to say. So out of the CFT, you see, for example, here, the CFT has modules for every M half integer, so to say, in the Ramond sector. But this length here only picks out, 1/3 of those modules. And depending on how you tune that, you either have, 1 or 2 or even no ground states. But the field theory knows about this Witten index, and that matches quite nicely.
The CFT has n equal 2 has a lot of sectors. So there's Nebo-Schwarz, Ramond, but there's also the twist sector. So how shall I compare who is whom? I mean, who is Nebo-Schwarz, who is Ramond?
So if you take purely boundary conditions on a closed chain, that's the most symmetric choice. Those are Ramond sector states. If you twist by some amount, you do spectral flow essentially. And if you go 20 periodic on the chain, you actually hit the Nebo-Schwarz sector.
So all these are Ramond states.
Right. But so you see, the Nebo-Schwarz technically, in my sense, breaks the supersymmetry. I cannot write it as Q dagger Q, which because the appropriate energy notion. So the lattice energy here is like the L0 of 0 minus 1 of 16 or so. So that goes negative in the Nebo-Schwarz sector. So it's interesting to study those, but they in the precise sense they break the supersymmetry as I have it here. Okay, so now let's do this 2D thing.
Can I ask about this delta equal to minus 1/2?
Yep.
So there is this Razumov-Stroganov conjecture, right, about mapping to alternating sign matters.
Right.
Do you see this in your spectrum?
Right. There's similar stuff. So there's sort of number theoretic magic in let's say, for example, the grounded wave function at xxz delta x minus half. There's similar magic, a bit different, but similar in our situation. So there's a paper by Kareljan about this. So I think they conjecture, for example, if you take the ground state, you see if you put this thing on an open chain of length 3L, so suppose you, where are you? Okay. So suppose you put this thing on 6 sides like so. Then there's a ground state supersymmetric with 2 particles. The most probable configuration for these particles is to sit here and here. It's kind of obvious. This is the dominant contribution to your ground state wave function. And I guess the least probable configuration to have them, for example, here and here. Everybody else empty. So there's a certain ratio of the amplitudes of these contributions to your ground state, which is some crazy number if you make this a very long chain. And so there are conjectures for what those numbers are. I think Paul Schoutens also looked at this and understands some of those things. Yes, like. Okay, so let's briefly go to 2D. Let me give you some of those crazy numbers. So here is 2D triangle lattice. Let's make a table of the width and indices, which is the easy thing. I can't make a table of the ground state degeneracies, which is a hard problem, but I can do this here. So actually, I started this at on Sunday afternoon.
How do you compute?
Using a transform matrix, I put it on the computer essentially. So
What do you do?
we do a transform matrix. So we start with let's say a 1 by n system,
Okay.
and then we do a transform matrix to go to 2 by n, 3 by n, etc.
How do you count -1 to the n?
By tuning the transform matrix to do precisely that. This is sort of a classical StatMan evaluation, right? So it's
Configuration.
Of what?
What you put here and there again. Right?
yeah, it's really recursive. So you for let's say 1 by n, you keep track of enough information, and then you do an iteration to go to 2 by n, etc., etc.
So the only non-trivial thing is that you have a restriction of that space of states that you have to implement, right? Is that the thing that's...
Yeah, so this is not trivial, but it's not too difficult to implement to put it on the computer.
Because you don't need a Hamiltonian to complete that.
No. It's a combinatorics counting problem, as opposed to diagnosing the Hamiltonian.
Exactly.
So actually, I started this on a Sunday afternoon, and got a few numbers like this, and then I got tired and asked the students to make a big
you
table.
really get
Yes.
integer. I mean, you do your computer, you get 5.
Yeah, so I'm counting. So I'm counting how many configurations do I have as an even number of particles, and I subtract the number of configurations with odd number of particles. Then I have integer, obviously.
There is a local rule. When you go the value here, you can have it there, right? That's the rule, right?
Yeah.
Then you just count.
Just combinatorics.
Yeah.
Yes.
So this is, sort of relatively easy, no sign problem, whatever. You simply do this. Again, I did this myself for small systems, and then I had a master student who did a project to do big systems, and so he got these numbers. Okay. And again, these are lower bounds to the number of ground states. We know there's actually more ground state than this, and then we don't know the rest of it. We don't know exactly. We know this is exponentially growing. At least that's strongly suggested by looking a bit better. But we don't know the actual solution to the counting problem here. It's an open problem. And quite a few people, including a strong mathematical friend, tried their hands on this, and so far it resists our temptations to our attempts to actually solve this. So this we call super frustration. Somehow these systems are tuned. So supersymmetry doesn't guarantee something like this to happen at all, right? It makes doublets, and that's what it does. But somehow, by imposing supersymmetry through this stupid and mumble construction, we hit Hamiltonian on this 2D lattice, which does this kind of magic. And this is so if you think physics, what's going on? These are particles. They are strongly repelling. They avoid each other on these neighbor sides. They push each other away if they are a bit farther. They hop around on the lattice. They are at some intermediate density. So these ground states live around 1/5, 1/6, 1/7 density. So this is strongly interacting. Intermediate density correlated electrons, fermions, and they do this kind of stuff. So there's something magical going on here, which we haven't quite understood. Here's the square lattice. So we thought, this will be a similar table, but it's not. This is again a table with big numbers, but they're not as big as the previous table. And there's lots of ones, and there's lots of structure here. So we got this table with Paul and the same guy von Eerten, the student. And we looked at it for a long time, and we saw all kind of patterns, which I guess are not very difficult to see. For example, if things are co-prime, the 2 dimensions, you get a 1, and there's other patterns that you can see. And then we didn't know what to do, and we essentially gave up. So we published this stuff in the paper, and we said, somebody look at this, because we don't know what's going on here. And then came a paper by a mathematician, Jakob Jonsson from Sweden, who was, I think at the time still at MIT, and he actually solved this thing. So he said, I have a formula for the written index if I take periodicities U and V, which are a bit more general than our n by n construction. And he said what you need to do is, forget about particles and quantum mechanics, put tiles of these two shapes on your let's say torus, the torus defined by the U and the V periodicities, and count those. And count the configurations of an even number of those tiles, and with an odd number of those tiles, subtract them like this, add a little correction, which is 1 or 2 or 4 or something, and that's the written index. So he reproduced this entire table from counting tilings on these square lattices.
Is that any easier than the way that you did it?
Yeah. Well, this is easier. I mean, counting these tilings, it turns out if you want to determine tilings, it suffices to fix them here and fix them there, and then on the inside everything is already fixed for you. Which shows that actually the growth of these numbers is not extensive, but it's sub-extensive. Okay, so but this is the written index result. It's not what we want for the physics, which is the number of ground states, but you see if W is T minus T, then the suspicion which we correctly had was that the number of ground states is T plus T. So we conjectured and then proved that the number of ground states for these 2D systems is actually adding, even an odd number of tilings with a small correction here. And this is a rigorous result, so this is quite a nice result. Every time you find a tiling that works, you find a ground state in a quantum problem. And you see from this, this is all kind of interesting stuff from here. These guys have area 5, this area 4. So if you only use the red tiles, you make a quarter-filled state. If you only need the green tiles, it's 1/5 state. If you mix them, it's somewhere in the middle. So you have ground states at different particle numbers. And there's a kind of peak if you look at entropy at the equal mixing, 2/9 filling. So there's all these things, and this is well controlled by this strong result here.
Normally in supersymmetric quantum mechanics, the number of ground states is equal to the written index, unless you fine-tune within the space of supersymmetric models. So it's very non-generic to have extra ground states beyond the ones that saturate the written index.
Right.
It indicates something extra special must be going on, but
somehow that extra special thing has been built in by us.
There's no parameters.
In these 1D cases, usually the W equals the number of ground states, but in these 2D cases are much more wild, and we see stuff like this happening.
So these models, there's nothing you can add to them that preserves supersymmetry, that would lift these extra ground states?
Probably you can. What I mentioned, there's this thing on the idea of staggering. So if you, in the definition of the Qs, you give a weight alpha I to the contribution from side I, you don't break anything. So you keep supersymmetry written index, but you do change ground state structures. So we didn't explore such things, but probably you can do that.
The boundary conditions, do you ever fiddle with the, it is all periodic?
This is all very fragile. If you take an open patch to the square lattice, single ground state. And so we have all kind of conjectures. For example, if you do that, if you go to this open boundary, there's probably all kind of edge current running around the edges that are kind of the remnant of these bulk degeneracy if you don't do that.
And do you know what the tiling looks like in that? Or does the tiling picture not?
Well, if you wish, the tilings never fit. They have to match the boundaries, and they don't. So, so you can play with all kinds of further details. But we first went back to 1D to learn more about what goes on there. So let me actually descend back to 1D and give you more information there.
Is there an obstruction to doing triangular lattice discounting?
We tried, the tiling approach. Also with Jakob Jonsson, we sat together and we invented all kinds of beautiful tiles, and we got some of the ground states covered, and never the whole story. But one of you here should be smart enough to make progress there. It's a very cute combinatorics problem. Actually, the secret also how we proved this thing, which was Lisa Huis's masterpiece for her thesis. The problem smells like cohomology, right? If you think Q is like X in a complex, Q squared equals 0, you're looking for states which are killed by Q, which are not the Q deck of somebody else because they shouldn't be in a doublet. So it's a clean cohomology statement. So if you wish, technically you have these graphs, they have an independent complex, that comes as a cohomology, and that's what we're computing here. And then there's all these tricks that are in the cohomology books, like spectral sequences and tic-tac-toe lemmas, etc. And that's how we did this in the end. That's the mathematical rounding up of this problem. It's quite magical. So a recent project was actually a bachelor student. Yes, that put this thing on the platonic solids and compute number of ground states, and then he did some smart stuff with the cohomology there, and he got the answer in a very, very smooth fashion. So there's beautiful math behind all this, but again, let me go back to 1D because that's where I have a few more things to say.
Get whether this degeneracy is a plus or a minus of the theory. So what is your point?
Well, as a physicist, you know you're looking at something highly tuned and non-generic. Probably this you'll never see happen in front of your eyes in an experiment. But of course, if you're close to a situation like this in terms of parameters, you're probably looking at lots of low-lying states, low-lying bands, and you may learn stuff about those.
So I guess it's non-generic and locally interacting system to have a thermodynamic number of ground states. Yeah?
Right. I mean, it's against the third law. Right. The third law tells you generically this never happens.
Yeah.
You have to tune stuff to get there.
And then some special physics happens around these points.
Right. And of course, it's in a sense, we're more used to, let's say, frustrated magnets, which have lots of ground states classically, but then quantum mechanically you break that, and there's a single one, singled out, ordered by disorder, stuff like that. Here it's like the opposite. Quantum mechanics stabilizes this whole big manifold of states. And you have to actually break explicitly this Hamiltonian to single out special states. Okay, let me go to this MK in one dimension then. So this is a modification of virtual definitions, which is kind of obvious. Rather than saying I only allow single fermions without any neighbors on the 1D lattice, now I allow up to k of them to sit together and form a little cluster, so to say. And if you do that and you try to add one more particle to a configuration, there's lots of cases. And in a sense, you have to specify the amplitude for having a situation like this. So you add a particle at position B to build a string of length A. So there's a whole table of amplitudes lambda sub AB times these creation operators. And you have to choose them right to have Q squared equal to 0 in the first place. And within that space of choices, there's critical, non-critical, etc. choices. So now there's a big space of supersymmetric models that you can actually move around in and play with. So there's some special nice choices which were kind of studied and discovered, in particular by Hagendorf and Huijser working together. So in particular, if you look at this MK model, there's choices of these lambdas, where you do a staggering mod k plus 2. So on the lattice, you take these couplings to repeat modulo k plus 2, but with certain strengths. And if you do that smart, you can make the whole thing integrable for, let's say, a given choice of a lambda, which is a unity, and then you can move away in this staggering and keep integrability, but go off critical and reach some massive phases. And so for the M2 model, which is the first where this is non-trivial, this is a rather easy thing to do, the staggering. For, let's say, M3 and higher, you need to be very smart, and there's actually lots of mathematics going into discovering which choices you have to have integrable lines of parameters available.
What do you mean by integrable?
Integrable, I mean, there's a beta answer, there's the standard notion that we all
What kind of parameters did you get? Do you have the master?
I guess, well, there's the, I'm not sure the R matrices. There's these Q systems, there's Wavy equations. I mean, every time, so the critical cases, you see, I mentioned M1 maps to x like t delta x minus half. The higher case map to similar spin models with higher spins, right? So you get spin, k over 2 rather than a half. And there are some, those are known models, and we actually could discover which of those are critical and map that back, etc., etc. So let me give you a few quick facts again. If you go to the closed chain, now there's this k plus 1 ground states. Set it filling k of k plus 2, so if you k of 3, that's 2/5 or 3/5 filter, etc. The critical case, is now the kth minimal model of n equals 2 CFT. So So if you wish, it's U1 times dk per fermions, or if you wish, it's SU2 level k, but then deformed a bit to become supersymmetric rather than SU2 symmetric. If you move away, so lambda less than 1 is the staggering that opens the gap. There's RG flow, you get a massive integrable field theory, and that's one of the famous ones studied long ago by Fenty Filligator company. This Lambda-Ginzburg potential, superpotentials of Chebyshev type, which are the magical integrable n equals 2 massive QFT. So we land on precisely those, which is actually quite remarkable. And to have that, we need to tune these staggerings to be very special, and then to precisely follow the integrable path, so to say.
Sorry, this theory is a solidon. So can you interpret?
They're kinks, moving around in
kinks
between.
yeah. Can you have a graphical representation like on the tiling before to represent that?
Sort of. I'll come to that. Maybe if you hang on, I'll. So what I decided to do for the rest of my talk today, I mean, there's lots of things to explain, but I try to zoom into, let's say, one of these models, let's say M2, which is a bit beyond M1, but not too complicated, and in particular focus on all these QFT connections, because there's quite a few of them, and some of them are, in a sense, better than we're used to. We're used to comparing lattice models to quantum field theories, and we usually understand a bit how you get from one to the other, but there's always lots of details. In these cases, actually, things are quite tractable, and supersymmetry helps in doing those things. So, my student Tessa Fokkema just completed a PhD thesis on all this kind of research. So here's a diagram taken from one of her chapters, where she brings this up. She says M2 model the critical case. Staggering makes it off critical. Critical case corresponds to CFT. If you stagger on top of that, you go to this massive field theory, which in this case is a supersine Gordon. So I decided to kind of follow this presentation and give you some of these connections in a bit more detail. So I'll show it like this. Here are these 4 corners. I'll give you some of these connections. So let's do the first standard thing. Let's take this M2 model. Let's tune it to criticality, which, if you wish, is like taking a spin 1 magnet, XX, Z, where you can tune things so you go critical, like the Heisenbergs. You have to work for the Heisenberg spin 1 to go critical, but you can do that. Similarly, we have worked to go critical for M2, and we are here. And let's look at some spectra and then see how the CFT pops up there. So this is a numerical spectrum. This is an open chain of some length 25. Particles here. So you see, spectra, which already for small systems, clearly manifest the conformal field theory structure. So in this case, the field theory is a U1 boson, so to say, times an Ising factor, C equals 3/2. So there's psi's and sigmas coming from the Ising sector, and there's VMs coming from the U1. And it turns out if you sit on a certain open chain, again, the U1 charges are dictated by the fermion number and the lattice length, half filled, so everything is like 2F equals L. And there's this selection rule that depending on particle parity, you pick out either the 1 or the psi modules of the Ising sector. So this is nice, you can keep track of these. This is the 1, 1, 3, 5, those are the canonical towers of conformal states. So that's nice. So you see, you only pick out a subset of all possible U1 Ramon sectors of the CFT. So if you take open boundary conditions, you're only selecting special choices. And we wondered, for example, there's more modules somewhere in the middle here. How can you get those? Clearly, you need to play with boundary conditions. And here is actually an interesting choice of boundary conditions, which turns out to be quite important. You see, we decided for this M2 model to forbid, or to allow 2 particles to come next to each other, but not more than 2. But now you can say, well, let's, for the first 2 sides, actually, forbid this once again. So let's take, let's say, an M1 boundary condition in an M2 model. Okay. And if you think about that, you see this model is half filled. So in a sense, a single side corresponds to half a charge. And what this thing here does, in a sense, it blocks half a side. You don't block the final side, but you block it sort of effectively half of it. So it's like a quarter charge rather than the half charges that are more canonical here. And because there's some people here who looked at not really quantum Hall states. If you think more read quantum Hall state physics, half filled, the usual quasi-particles of charge are half. Those are which single sides on my lattice. And the guy that I enforce here actually has the quarter charge. So it's the quasi-Hall with the quarter charge, and we know that comes with a sigma field if you think Ising. right? So in the same, following this intuition, we kind of anticipated that putting these kind of boundary conditions frees up, opens up these sigma sectors of this CFT. And you can check that. So if you now draw spectra where you say, for example, I put a sigma condition on the left hand, open on the right hand, you indeed get sigma times v times modules. So everything shifts a bit from where we 40 were somewhere here, now it shifts a bit to here. You also see there's a shift in this. There was a half here which is now gone. And if I put sigmas on the two ends, that's kind of funny. So you go back to 1m psi modules, but now you see before I had either 1 or psi for a given Fermi number, now I have both of them. So what happened, I put sigmas on the two ends by doing these funny boundary conditions, and sigma times sigma equals 1 plus psi, and you see kind of an abelian fusion happening here in these spectra, which I guess is not too surprising once you understand that our microscopic choice of boundary condition is like a sigma field on the end, it's like a boundary condition in the CFT, and if you have two of those, there's all the Cardi rules that tell you what kind of modules to expect, and you see this kind of nice rule play out in front of your eyes if you follow these spectra. So that's nice, and you can really convince yourself. We actually repeated this for the M3 case, where you get all the C3 parafermion magic, and you can actually inject parafermion spin fields at the two ends as you like them. So that's quite cute. So there's a standard thing, you go to a critical lattice model and you discover CFT things. Here's a non-standard thing. Let's start from the CFT and move backwards. This is actually how historically we first arrived at these MK models. So the logic we entertained when we started this was, let's somehow try to build a lattice model which by construction is supersymmetric. There weren't any at the time around, and the idea was let's take a field theory that's supersymmetric manifestly and somehow finitize it to become a finite lattice model, preserving the supersymmetry, and see what we get. And this is how we first got all these M1, M2, etc. models. We never published that until recently, so now I put out a paper with Tessa Volkerma a few weeks ago where we actually wrote up how we do this. So this is this finitization, which is actually also mathematically very interesting. So what do? We learned these things from Duncan and friends who made these connections in the case of SU2 level 1 Westermino-Witten as compared to, let's say, Haldane Shastri lattice model. So in particular, this paper, including Denis, as an author, was make these connections very clear. So what do? So you look at your CFT, but you don't use Fusorial algebra, F1 Katsumuri, but you say, well, there's fundamental filter excitations, which are these spin-on fields, and if you pile up those, you can actually cover the whole spectrum. So you think in terms of single spin-ons, 2 spin-on states, 3 spin-on states, and you try to build your entire spectrum, and you try to discover the rules how to do that. So that's Duncan's business with motifs and all these extra rules he discovered. So if you do this special case here, you make multi-spin-on states, you can discover their SU2 content by applying this sort of generalized Pauli principle, which tells you that if you choose your ends in a certain fashion, that gives you a certain SU2 content of that state. If you take all these ends widely apart from each other, you get essentially the doublet. This is a doublet field to power n. But if you take them closer and closer, you start losing states and you get restrictions. So those are these motif rules. So these have been figured out actually using all kinds of mathematics, in particular Youngian symmetry and representations thereof, to make this precisely happen. And you can reproduce, let's say, CFT characters by applying these rules and working it all out. And then the funny thing is, once you have this in place, so let's say a new way to organize CFT spectra, you can say, well, if you now cap the momenta, so these ends here, so you give them a maximum value, something like this here, that reduces the whole set of multi-spin-on states to a finite set. That's a finite partition sum. Capping momenta means like you put a minimal distance. So if you think unit circle, and cap momenta, that means they have only n points rather than a continuum. And it turns out if you do this in this case, you cap the n's at this value here, you discover, the spin a half on L side type partition sum. If you wish, the Haldane Shastri model itself. So this is a different way of thinking, right? So you understand the field theory in terms of fundamental excitations, you pile them up, discover how they have exclusion statistics if you wish, then you cap their momenta, and here comes your finite lattice model. Okay? So here's some of the way this is done. So for example, these are choices of these various ends, and then you can count degeneracies, see what SU2 content that gives you, blah, blah, blah. And this is Duncan's famous notation for how you organize these things, these rapidities. So the 1, 3, 5, 7 is the CFT vacuum. If you take some of those numbers out and you do little shifts, those are the spin-on excitations. Okay, so now our plan was, having seen and understood all this, to actually repeat as much as we could the same construction for the new situation with the supersymmetry choice. So we take this CFT rather than the other one, and we try to repeat the whole thing. So rather than a spin-half doublet of spin-ons, we took a SUSY doublet of spin-ons. So it turns out, we take U1 charges minus a third and plus 2/3. They're connected by our supercharge. So these are the full dimensions. They're different by a half, which is canonical if you're a SUSY doublet. And you can, build multi-spin-on states in this situation here. So you can make n spin-on states. There can be up to 2 to the power n components if you multiply all these things out. There will be less components in general if the spin-on momenta are close together. There are certain rules for how that works. So there's, let's say, a new Pauli rule, a new motif rule, which we figured out, and we got that to work such that we correctly reproduce these CFT characters to arbitrary depth. And then, having all this in place, you can truncate you can cap the spin-on momenta. So that makes your model finite, but, and that's the important thing we put in by construction, you never lose the supersymmetry. Because if you cap the doublets as a doublet, you never lose one and keep the partner, so to say. So this construction had to result in an n equals 2 supersymmetric lattice model. And so we simply did this with Bentley, and we found partition sums, and we stared at them, and then we discovered that we could match them by imposing this funny exclusion rule that I introduced a bit earlier. Okay, so and then we discovered there was a natural Hamiltonian, and everything could be made to work. So, but there's something non-trivial going on here. And in particular, there's beautiful mathematics underlying this SU2 level 1, Halden, Shastri, Yangian, etc. Some of that we could make to work in this case as well, but not quite. And I talked to Denis this morning to put all our open questions there. There is, something like a Halden, Shastri, Hamiltonian at the level of the CFT. We know it's spectrum. We can diagonalize with multi-spin-on states. We can move in those spaces using supercharges and higher versions thereof. But again, it's a bit harder than in the SU2 case to control everything.
Is there any analog of the Yangian part of the story?
Sort of. So the Yangian for SU2, you have the SU2, let's say the bottom level, and then there's all these QA sub L. We have similar stuff. So we went one level up and produced supercharges of the next level, so to say, which anti-commutative give a new Hamiltonian, this Halden-Shastri type Hamiltonian. But it's not as clean as in the other case. So we struggled a bit, and it's sort of half done. Okay, but then you can actually. So here's a table. So this is actually everybody of this multi-spin-on base is contributing to the L equals 5 partition sum. And you can see, for example, this notation is again like the one Duncan always has, but now he spaced his integers by steps of 2, 1, 3, 5, etc. He spaced them by 3 because we deformed everything to go supersymmetric. And this is actually, the fact that this works so nicely is quite rewarding. Okay, and if you make this correspondence, you can look through these things. For example, this state here in the CFT would be the empty chain, 5 sides, no particles, and this guy here, which is the CFT supersymmetric ground state, actually becomes in this finitization the SUSY ground state of this model of 5 sides, 2 particles, etc., etc. So understanding the CFT before finitization, for example, steers you straight to the lattice model ground state, and so it really has some predictive power. Okay, the K equals 2 case, you can also repeat the same logic. Now, there's a complication, which is that these spin-ons, which are again phi something, they actually carry, in this case, an Ising spin field, which means that if you pile them up and you make multi-spin-on states, you have to keep track of fusion passes of all these sigmas. So there's what we had before, plus some Bernoulli diagram business, and things are a bit more complicated. We looked at this before for the SU2 level 2 cases, Wagner Ludwig, and we figured how these things work, and a similar construction works in this case here. You cap the momenta, look what you get, and you get this M2 monopartitions, and you discover this, this modified exclusion rule where you allow 2 particles next to each other. So these things are quite magical, and for example, these funny sigma type boundary conditions, you can also get those. So those partition sums you can also get from finitization by tweaking a little bit how you do that, and so that's quite nice. We're actually trying to use once again the same strategy to discover some models with spin-half fermions with nice supersymmetry, which are not around yet, but that's in progress. So this is here's a table of how we do these things, and here you see this is the fusion passes that we have to keep track of to get things right in this reduction. A few more things. So I discussed about the critical lattice model, critical CFT, how you go from one to the other. Now let's look at staggering. So let's do the M2 model. and let's look at this integrable staggering perturbation to modify the model, go massive, and see what that gives. Now, in this case, the staggering is actually extremely simple. It simply means that you give a weight lambda to all the supercharges on, let's say, even sides, and a weight 1 on all the odd sides. So this means, if you make this lambda go down from 1 to 0, you in a sense decouple all the odd sides, and the model trivializes into product states. Okay, so we know there's an easy limit, but if you take lambda slightly below 1, it opens a gap, and you get interesting physics. So, for example, this bit with these sigma fields that I can put on the ends of my chains, if you use the other lingo, this would be, my random zero modes that at the critical point are delocalized, so they extend over the chain. But as soon as you open this gap by staggering, you localize these guys. And so there will be degeneracies coming from localized Majoranus at the ends, as we've seen in other situations. So I'll show that in a second how that goes. And then again, if you send lambda all the way to 0, and now I kind of answer Giuseppe's question, you get kind of tiling pictures or simple product state pictures. So there are now 3 ground states, which is the Witten index for this M2 model. For example, this is one. If you decouple the supercharges on the sides where there's a 1 here, they're still active on those sides, but they can't do anything. They can't take away a particle, and they can't add a particle because that's forbidden by the rules. But this is a manifest ground state. And these guys are as well, they're slightly entangled still, but in a very mild manner, and then you build up these things. So there's 3 ground states at extreme staggering, and there's a nice physical picture, which somehow smoothly connects to the CFT if you go all the way back to lambda equals unity. So now here's some of the physics. So here's again a spectrum. This is this chain, open chain, sigma sigmas at the end, where you got this spectrum, and I mentioned, sigma times sigma is 1 plus psi, so you get these two possible fusion channels. They're split by 1 over L because it's a critical system. But if you kill the criticality by the staggering, you expect these guys to merge essentially on degenerate ground states, and you get some kind of qubit where there's a sigma sigma two channel situation which will be degenerate in energy. So that should happen, is the expectation, as soon as you put on this lambda, away from 1. So here's how that goes. Here's the spectrum that I just showed. Here's this lambda, and if I turn it down all the way to 0, you see what happens. You need to collapse these 2 states to become 2 degenerate ground states. So this splitting is exponentially in the lattice length. And if you look carefully what these states in the end are at extreme staggering, they're these 2 patterns, which are now, they actually fit to the boundary. So the sigma type boundary conditions needed to make these guys have a happy match with the boundary situation. Okay, if you take all boundary conditions, you lose either one or the other, and you never have to dot that. Okay, so this is, in a sense, a nice little manifestation of what this gapping out does, and how the Ising feeling can be understood here. If you look further at the spectrum, there were some arrows here which I'm not showing. You see also these kinds of things at extreme staggering, and these are obviously kinks, kinks that connect different vacua. So for example, here is an example. So if you start from the left with one of the vacua, you continue with another one. In the middle, you have to match them, and that's a place where supersymmetry can act. So if you put a 0 here, supersymmetry can make it into a 1 and vice versa. This is a doublet, energy unity. And those are the guys you see here at extreme staggering. These are 2 kinks, 3 kinks, etc. And all these things can be understood. So in the end, there's 8 types of kinks. So you can go from plus minus to 0, or the anti-kink for that, or you do it in the other direction, or the anti-kink for that. And you can play with those things. So they're fermion number half minus half, so they're super partners, fused as one to the other, and all that structure is very tractable. If you move away from lambda equals 0, these kinks become mobile, so they start moving around with some hopping amplitudes, and you can look at that, and you get a simple band dispersion if you keep lambda small enough. Okay, so that's, in a sense, a nice extreme corner where things are very tractable, but still connected to the original model. Now here's another, reversing the logic situation. If you know what you're doing down here, so you know your ground states, your kinks, exclusion, how close kinks can come, etc., you can do a lot of counting down here, Q-deform that, and you find back your critical model here. So that's actually quite a nice thing. So, we analyzed how this kink counting goes, and again, there's this Moore-Reed quantum Hall connection. So counting these kink configurations is pretty much the same as counting excitations. I mean, how many ways you have to put non-abelian quasi-holes over Moore-Reed states. So if you do more read on a sphere with so many particles, so many fluxes. There's counting problems that were addressed by, for example, Nick Reed and Ed Rizai. Essentially, that same counting problem applies to the king situation here. And if you do all that and you Q-deform that counting, back come your conformal characters. So you get all these expressions. For example, this is a case where I put n kings and bar anti-kings and give me a certain charge in the CFT. And I count how many ways I have to do that if I have on L sides. And there's this kind of way. So there's a factor for kings, factor for anti-kings, and then a factor for the, let's say, the Bernoulli diagram aspect of these things.
Is this integrable model like N1 super sine Gordon?
Yes, it's coming. This is like the cartoon version thereof, because now I simply followed my staggering to the extreme corner, where I'm not relativistic, I didn't follow RG, I simply followed the parameter. That gives me this kind of business. And you see, it's kind of nice that if you understand well enough what you're doing in that corner, you can resurrect all your conformal structure by essentially doing a counting problem that we knew how to do from quantum Hall situations. Okay, now here comes, I guess, the question of Alexei. If you do the sort of the more physical thing, which is put on the staggering perturbation and let RG work for you and see what QFT that gives you, that's indeed super sine Gordon. And another way to get there is to first interpret what happens here as a CFT and then perturb it with the appropriate operator that corresponds to the staggering perturbation, and it gets you in the same corner. So now this is actually an interesting place. So you end up in SUSY sine Gordon, which means n equals 1 supersymmetric sine Gordon. But the thing we started from was manifest n equals 2 supersymmetric. So this is highly confusing. And in the end, the conclusion is you have both. So n equals 1, comes with the field theory. In a sense, it's emerging in the RG flow. And n equals 2 is coming along for the ride manifestly and never changes. So in the end, you find yourself at a special point of super sine Gordon, where there's, in addition to n equals 1, there's an addition n equals 2 supersymmetry. Which is precisely the point where the kink anti-kinks have fermion number of half minus half, and they connect via the n equals 2 supersymmetry. So this is a special point where you have to be because of all the things we put in. And then you can actually,
I didn't understand. Are you ordinary sine Gordon at that point is supersymmetric or supersymmetric sine Gordon? It's a different story.
Okay, if you take the M1 model,
so
yeah, sorry.
you have an equal to supersymmetry, and then you have an equal 1 supersymmetry from the diagonal. Again. Usually in sine Gordon you have a special value, so you have an equal to supersymmetry.
N equal 1.
That sounds like, so here you go. So if you take this M1 model, so which was the C equals unity CFT, and you do staggering perturbation, you go to regular sine Gordon, nothing supersymmetric, but at the n equals 2 point.
Okay.
Which is beta squared equals, I don't know, something special.
Okay.
So
Now, if you do, the M2 model, you C equals 3 half CFTs.
Okay.
So you go to super sine Gordon, which already has n equals 1, but then you also have a special point where there's n equals 2 in addition. And everything is present in the end. And if you make this connection, you can follow through and do all kind of nice exercises. For example, these sigma type boundaries, which are kind of the magical things that freed up our sigma spaces. If you follow them, they end up corresponding to certain boundary scattering processes in the super sine Gordon. And you can look at what those are. They are kind of the non-diagonal boundary scatterings where you mix factiva at the boundary. And so you can look into those things and kind of make the picture complete by using, translating all the stuff we know microscopically in the M2 model to the things we would like to say in the field theory, particle formalism, etc. And again, so the funny thing, I showed you these 8 kinks in the extreme staggering picture, which was this kind of cartoon where everything's very simple, factorized ground states, kinks that we can actually count on our fingers and everything like that. The actual super sine Gordon particle picture is extremely similar. There's 3 ground states, there's kinks connecting all of them together. So in a sense, my view is that this, I guess that's my last thing, this extreme staggering corner of the M2 model is like a cartoon version of the actual relativistic field theory that you have over here. It has many of the features sitting there, but of course it doesn't have the relativistic space-time structure and all that, which only arises if you actually follow an honest RG rather than simply pushing a parameter to a special corner. But it is rather special. I mean, we followed, for example, we looked at higher MKs, we looked at what we get here, and we get precisely the particle spectra that we know for this Chebyshev type n equals 2 field theories. So this is not a coincidence, but it's a systematical structure that we're uncovering. Okay, I think I should close. I decided to give you 3 little thoughts to, to take home or whatever, take to your office. I think one thing I would say, if you look at these MK models, the lattice model, the field theory correspondence is particularly rich. So we can sort of go beyond what are the usual ways to compare the two sides. I think this is important. I didn't bring this up at all, but the magic of the supersymmetries will also play out if we go beyond equilibrium and look at dynamics and things like that. I think I should talk to Vladimir to learn more about this. And then, again, what I mentioned rather shortly, all this 2D stuff, I think this begs for further analysis, both at the level of the mathematics, simply how you count these ground states, and the physics. So what are we looking at here? How stable is it if we add little perturbations? What are we looking at in terms of physical phases of matter? So that was my story. Thank you for listening.
Did you look into entanglement measures? Area, volume law?
Yeah, in the 1D case we did the standard thing. So we looked at bipolar entanglement, and we confirmed central charge and things like that.
This super frustration, does it lead to some kind of special?
That we didn't do. The 2D case, that's all open. Clearly, if you go into that, you'll have to decide in which ground state you actually do your analysis. No, I think there's many things to be done in those cases. You see, we looked at quite a few other 2D cases to understand better what's going on. In the end, there's this situation, I think, which is quite common in mathematics, that there's kind of 3 classes of behaviors. There's finite, there's tame, and there's wild. So mathematician told this. So finite are some cases also in 2D where we tune to actually, a finite number of ground states. For example, if you take the following 2D lattice, you take square lattice, say, and you decorate it by adding 2 extra sides per link, like this. So then it turns out if you do the M1 model on this lattice, it is non-frustrated. Because in the 1D case, we kind of understand that what the system likes to do is put a particle every third side. It's 1/3 field. This is dominant in the ground state. And you can do the same here. So for example, there'll be a configuration like this here, which will in a sense carry a type of ground state, which should set filling 1/5. And another option you have is to put actually 1 particle on each of the links in a certain way, which sits at a filling of 2/5. And so this model has a crazy feature that if you plot energy against filling, there's one ground state at 1/5, one at 2/5, and everybody else is finite energy. So this is like a finite case, although probably what you have down here is very low in energy. And then there's the tame case, which is like a square lattice, where there's extensive entropy in the length of the circumference rather than the area. Then there's the wild case, which is extensive in the area. And you clearly these things are very different categories of behavior. And for example, the simplest, let's say, wild case, you don't even have to go to 2D. So it turns out if you do M1 model, same as always, on this simple zigzag ladder, it's already a wild example. So this actually has entropy growing with the length of the system, and we don't understand this one here. So I guess this would be the thing to try first, understand more about this very simple model. We understand, we can do the counting there, the counting, but let's say what's going on physically here. Also the dynamics and entanglement, blah, blah, blah. We don't quite know. This shouldn't be too hard to give some further thought.
This is the one that was equivalent to XXZ at that time.
No, XXZ is a single chain, so where it's kind of standard and we understand pretty much everything.
Yeah.
But as soon as we make it slightly more complicated, we get into this new situation.
And one quadratic model with 4 supersymmetries.
Schemes.
Yeah, so that's something I guess I mentioned very quickly. So actually I have a paper with Santa Chiara where we tried some of this, and you were not too happy with what we got. So what I'm trying now, which is actually covered partly in this spin-on basis paper, is to take a CFT, which I know is about spin half extensions. So if you wish, my secret logic is that I mentioned a few times that there's this quantum Hall wave function connection, which is kind of behind the scenes of what I told you. There we know how to go from spin polarized to spin singlet. So it's got to go from more read to these monolithic spin singlet states, which I wrote some time ago with the Ardoma. And so we know what CFT that is, and we actually tried our spin-on basis machine on that, and we got it to work. So we actually have a spin-on basis and all the Pauli rules for that. And that suggests a road to these n equals 4 case. It won't be completely plain vanilla. So you'll end up with supercharges which carry spinor indices, and you have to write stuff like this here. So you expect some delta AB times Hamiltonian, but then there will be more stuff. And for example, there could be spin operators coming out of this anti-commutator. The most obvious things are not leading to interesting models so far, but there may be a way to do it.
Somebody show a spectra as a function of lambda. There was many crossing in this. Are they two crossing, or are they just no? Why there's so many crossing?
I guess there are two crossings.
Which means that there is something special, because usually crossing are avoided.
It's probably integrability, which is maintained all over this this lambda range. I think it's typically states with different kink number content, so to say, which are crossing, which don't mix so easily.
Because it's integrable for any value of lambda? I think it was just integrable.
No, integrability is maintained for the other lambdas as well. So
then
are there strong enough Razumov type of behavior in the CZ sign Gordon at the n equals 3 point?
you mean in that small version thereof, or?
Well, either side was said that somehow in the sign Gordon M1 they were related, or they both appeared.
Yeah, so I guess I would expect similar magic in, let's say, ground state wave functions for mk on some finite lattice. Which
The other side you don't know.
in the field theory, I'm not sure what I would look at, right? Because you follow these amplitudes and their ratios as function of the lattice length. If you extend it to infinity, I think you lose control there. This is really sort of highbrow number theory things that